An important application of the constraint optimization is in the utility maximization. Recall from your classes in microeconomics that your goal is to maximize utility, for example, from consuming goods X and Y subject to a budget constraint. In other words, we have the budget constraint here in green, and our goal is to try to maximize our utility, which is this point. The interesting thing here is that the gradient of the utility will provide us with the marginal rate of substitution. And then for the case of the income, remember that the slope will provide us with the ratio between the prices of X and Y. So this property that you have seen in microeconomics comes from actually a Lagrange optimization. Notice that the Lagrange function is simply equals to the utility function minus the lambda times the restriction, which is the budget constraint. Then we take the first order condition with respect to x, y, and lambda. And from that system is where we will obtain this relationship. In order to understand that better, let's solve the following example. The formulation of the utility for Ernesto is provided here, where X is a cereal and Y is milk. Ernesto has a budget of $28 and he wants to expend it in buying cereal, which costs $7 per box, and milk, which is $4 per gallon. We want to know what is his optimal consumption bundle and what is his optimal utility. In a utility problem, our goal is to maximize the utility subject to a budget constraint. Now, before we use the Lagrange, we can actually insert the prices and the income as given in the problem. In this case, the price for X, which is cereal, was 7, and the price for milk was 4, equals to the income, which is 28. Now remember that we need to have 0 on the left-hand side in order to insert it in the Lagrange function. To obtain 0 in the left-hand side, we subtract to both sides by minus 7x and both sides by minus 4y. In that way, we will obtain 0 equals 28 minus 7x minus 4y. So this is going to be our constraint, which must be equals to 0. Now, for this particular case, first let's set the Lagrange function. Remember that we need to put first the objective function minus lambda times the restriction. And this must be equals to 0. So in that sense, we are subtracting 0 from the objective function. So let's replace the values. So the Lagrange will be as a function of x, y, and lambda equals to the objective function, which is x to the 1/2, y to the 1/2, minus lambda times 28 minus 7x minus 4y. our next step is to compute the first order conditions. First with respect to x, then with respect to y, and finally with respect to lambda. With respect to x, notice that the constant part is y to the 1/2 times the derivative of the variable part, which is 1/2 x to the minus 1/2 minus lambda times the derivative of this expression with respect to x is simply minus 7. And for the first order condition, we set this equals to 0. Now let's continue with the Lagrange with respect to y. Here the constant part is x to the 1/2, and then the derivative of y to the 1/2 with respect to y is 1/2 y to the minus 1/2 minus lambda times. Here the derivative with respect to y is simply minus 4. And then this is equals to 0. Finally, the derivative with respect to lambda here is minus 1 times 28 minus 7x minus 4y. Again, this equals to 0. Now let's organize. This is 1/2 x to the minus 1/2 y to the 1/2. This is plus 7 lambda. We move it to the right hand side as minus 7 lambda. This is 1/2 x to the 1/2 y to the minus 1/2 equals to minus 4 lambda. And finally here you can see that this is going to be 7x plus 4y equals to 28. Let's copy these three equations in the next page. Notice that we cannot use the Kramer rule because these two functions are not linear. Instead, what we do is the following. We will divide the first two equations. From there, first you can see that 1/2 and 1/2 simplifies, and then notice the following. Here we have x to the minus 1/2. Let's move the denominator to the numerator. So this is minus 1/2. Y is to the 1/2, and this denominator, let's move it also. But because this is negative, when we move it to the numerator, we change the sign. This is equals to negative, and negative cancels out, and lambda also cancels out. So this is 7/4. From here, notice that this is going to be x to the minus 1, y to the 1 equals 7/4. In other words, this is y divided by x. equals 7 over 4, or y is equals to 7 over 4 times x. Notice that this relationship that we obtained from the first two equations will be replaced on the third equation. So here we have 7x plus 4 times, instead of y, we write 7 fourths x equals 28. So here we have 14x equals 28. So this means that x is equals to 2. Y is equals to 7 over 4 times 2. So this is 7 over 2, which is 3.5. Now that we have our optimal values, our last step is to obtain the optimal utility. And we can obtain it by inserting the optimal points. And remember that here we have that the utility is x to the 1/2, y to the 1/2. So this means that the optimal utility is 2 to the 1/2 times 3.5 to the 1/2. If you solve that problem, this is equals to root square of 7. So that will be our optimal utility when we choose the optimal consumption bundle, which is 2 boxes of cereals and 3.5 gallons of milk.